And so, when the James Webb Space Telescope was launched on December 25th, 2021, expectations were high that we would see many more galaxies from that lost epoch. Webb is an infrared telescope, allowing it to probe deeper into space and time than Hubble. When we look at the Hubble Deep Field, we can see a range of galaxies from many epochs. The oldest visibly red shifted due to the expansion of the universe. But while galaxies emit across the electromagnetic spectrum, when we observe the light spectrum from increasingly older parts of the universe, there will be a point where most of the light has shifted out of the shorter wavelength domain. Hubble cannot produce images of galaxies whose spectra have shifted out of the visible wavelengths. However, Webb, an infrared instrument, can see light from further back in the past because it can detect photons even if they have shifted out of the visible wavelengths and into the infrared. Able to look deeper and further than Hubble, Webb has already observed some of the earliest galaxies we have ever seen in the universe, just 350 million years after the Big Bang. But even this giant of astronomy has a limit. While the JWST has provided a fascinating view of early galaxy formation, to reach further, to reach the mysterious dark ages, we need a completely different instrument. Hubble, an optical telescope, and JWST, an infrared telescope, have provided tiny samples of the sky, both in image space and in time. To advance to the earliest moments of the epoch of Rayonization and the Dark Ages, we need the longest wavelengths we have, radio. As we look further back in time, we see more of the universe per pixel. So, while we can see the sun and galaxies like Andromeda and the whirlpool in exquisite detail, as we move to older times, the achievable resolution is so low that we cannot see individual stars or even individual galaxies. We need something on a much larger and radioluminous scale. And this is where the 21 cm hydrogen line of Van de Hulst shines. As we have seen, in the early universe, hydrogen clouds permeated the universe, and these can provide a means to observe the progress of the epoch of Rayonization, the 21 cm line. We can observe the Dark Ages as a cacophony in the redshifted 21 cm line. Then, as the ionized bubbles grow and merge, we can track them in the absence of 21 cm radiation, like a cosmic Swiss cheese. The shape and speed at which they grow can tell us a lot about the sources producing the radiation. Population 3 stars, baby black holes, and even the earliest forms of galaxies. Radio telescopes hold the key to illuminating the Dark Ages, but the experiment is one of the most difficult in astronomy. The signal is incredibly faint, buried under the photons from our bright galaxy that inevitably fall into the same antennas. Is it really possible to find the signal of reionization and illuminate the Dark Ages? Imagine yourself deep in the Australian outback, in a desert landscape devoid of human life, the red dust interrupted only by rocks and dried shrubs. The powerful heat of the day shimmers in the dry air, with no sign of recent or imminent rain. But as you walk, you see evidence of life. Sheep and cattle grazing in land that humans generally consider too hostile to inhabit. These animals not only experience this land differently, but also see it under a completely different light. The lenses and sensors embedded in our retinas can result in vastly different visions and understandings of the same environment. Humans are generally born with cones sensitive to the colors red, green, and blue. But the cows and sheep you pass by cannot see the red tones of the earth. The snake slithering near your feet also cannot see the red tones, but has an ability that you do not. The ability to sense infrared. Here, you find another companion, as a scorpion moves ahead of you, weaving its way through the metallic forest. This scorpion can also detect UV light and has the rare quality of fluorescing when exposed to these wavelengths. The animal kingdom is full of examples of adaptations to different levels and wavelengths of light. In fact, humans are rare in seeing only in the optical. Instead, we mimic the animal kingdom by creating technology to help us perceive our environment in UV, infrared, and X-ray. We have also invented entirely new methods, not shared by any other being on Earth, to access the longest wavelengths, the radio waves. In the quest for long-distance communication, we built our own interface with the radio universe, learning by trial and error how to hear a signal from a different room, a different country, a different continent, and then, by chance, we picked up signals from stars, planets, and meteors, and radio astronomy was born. We developed the means to communicate with the distant universe and the distant past. Only humans can communicate in these longer wavelengths, having carefully created for themselves a new kind of eye. As you walk through the desert, you encounter a strange sight. On the ground, there are strange metal sculptures. Some are butterfly-shaped. Some look like reflector tables, and others resemble trees, their spikes evoking cacti. But these bizarre metal structures in the Australian outback are not discarded abstract art. They are an interface to a universe that only we have access to. They are a portal to the past, to a time when stars were just beginning to form in the densest nodes of that web of dark matter. On Earth, humanity has also woven a web, creating societies and cities that spread across the Earth. This spread is not uniform. Civilization developed around rivers and seas, driven by the need for trade. Over time, the most hostile terrains, like the desert, were abandoned by the promise of amenities and safety in numbers. For radio astronomers, aiming to detect the faintest signals from space, the quietest voids on Earth are an ideal location to set up their experiments. Deep in the Australian outback, covering an area of 49,500 square kilometers, Murchison Shire has a population of just 100 people. Here, in one of the quietest places in the world, far from human technology and interference, radio astronomers have spent more than a decade searching for signals from the Dark Ages. And in 2018, one of these telescopes received a very strange signal. This telescope is humble, even simple, and far from the standard image we associate with astronomy. EDGES is a radio telescope, the abbreviation for Experiment to Detect the Global Epoch of Reionization Signature. EDGES works like a TV or radio antenna, receiving radio waves and converting them into a digital signal. It is a sensor, tuned to that cosmological 21 centimeters line emitted from the epoch of reionization and the first stars. These photons have traveled to us from 13.7 billion years ago, so we detect these photons in stretched wavelengths from 21 centimeters to about 2 meters. By building a telescope on this scale, these wavelengths create a voltage across the telescope, producing a digital signal that we can examine to verify its origin and intensity. The telescope actually measures the temperature of hydrogen through the Dark Ages, tuning and observing at different wavelengths to scan photons from hundreds of millions of years. Although the gas is cold initially, coagulating around the web of dark matter, when the first stars form and begin to emit their own radiation, they heat their surroundings, imprinting a change in the 21 centimeter signal. Never moving, never making a sound, its human operators thousands of kilometers away, EDGES listened patiently. Even in one of the quietest places on Earth, the sound of humanity and atmospheric interference are too great for us to look at the earliest stages of the Dark Ages. While we continue to gather data, refine our models and methods, we also look to the next step. We seek quieter places, like the Moon. Tests have already begun to help send antennas to the far side of the Moon, using the Moon itself as a shield against the onslaught of cell, radio, and satellite signals. Only by seeking the quietest places can we truly know the darkest times, finally illuminating the cosmic Dark Ages. And so, the universe was dark for almost 200 million years, but really only to our eyes. For the metal antennas in the desert, our interface with the stars, there was never darkness, just a time of silent activity. Gas and dark matter worked together to form stellar nurseries, and in the longer wavelengths, the universe was bright with 21 centimeter photons throughout. But it was the explosion of light from the first stars that changed the universe from dark to light in the way we now perceive it. Stars would gather to form galaxies, long-lived and bright. So did you enjoy our journey through the beginning of the universe? If you did, don't forget to like and subscribe to the channel so you don't miss the next episodes. I'm Paul Edward, and this is Daily Science. See you soon, where we will continue to unravel the mysteries of the cosmos.